or silicon, etc. Okay, so looking at this, you need to know the atomic number of each one of these. I sometimes call this schnapps, all right? So you need to know carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Memorize the atomic number of these guys. You also should know the configuration of these atoms. In other words, how do the protons and electrons pack in? Now we call that, the way that they pack in means that how are they going to exist in terms of where the protons are and where the electrons are. Now right for this argument, I'm going to ignore the neutrons. Now the reason is because the protons and electrons are attracted to each other. In other words, I have the positive and negative charge that are attracted to each other, and they're the ones that are kind of glomming together. The neutrons are kind of, I always kind of think of those as spacers. They are helping make up the mass. It's kind of like the balls that you see in at McDonald's or something like that in the little play gyms. There's spaces between those balls, and those, in order to make a core that is stable, you have to have something that's filling in those spaces, and those are the neutrons. Now, in something small like hydrogen, this form of this atom actually has no neutrons, but even though I would ignore them anyway in this drawing. Okay, so anyway, this has one proton, or +1, and it's going to have one electron, or -1, and that is going to be circling around in what we call the first energy level. All right? Now, the energy levels are just the distance away from the central core that can happen. And they look somewhat like this. If this is the central core, the first energy level is going to be the first distance away. I'm sorry, this is the central core. This is the first distance away. And then the second, after you get this one full of the maximum number of electrons that can be as close to that central core and not repel each other because they are the same charge and would repel each other, then you're going to have, the next group is going to have to be a little bit further out, and that's called the second energy level, and likewise the third. So those are what the energy levels mean. Okay, so in the case of the energy levels, in this first one, there's only one energy level and only one electron. So let's look at this one, and maybe this will make it a little clearer. You have the central core that has a +6 protons. Those +6 protons, of course there would be neutrons here too. We would assume perhaps 6 neutrons as well, packing in with the 6 protons sort of in between them. Now this means that it has 6 electrons. And in the first energy level, that first distance away from that central core, there's a maximum of 2 electrons that can exist. And that they would exist in orbit exactly opposite each other. And this would make that orbit fairly stable in the sense that those electrons are not likely to be lost, all right, because they are together in an orbit, circling together, and other things are not as likely to interact with them. Now, in the second energy level, which is a little bit further out, because the electrons are repelling each other, they're as far away as they can be from these electrons, but they are still attracted to that central core. So they are trying to get close to that central core, but they are repelled by this level. So that's what makes them circle around. Now there are different ways to circle around in that second energy level, and these are called the S and P orbitals. In the second energy level, you have, well, in the first energy level, you just have one S orbital that can have a maximum of 2 electrons. In the second energy level, you have one S orbital and 3 P orbitals, all right? So what is happening, so this is representing that. What is happening there is the p orbitals look kind of like little figure 8s going off in different directions, and the s orbital is more circular but outside the first energy level. The way I've drawn it here is just sort of a shorthand way, and I'll show you in a minute another real shorthand way to draw it. But in this case, this is carbon +6. It's got 2 electrons in the first energy level. That leaves 4 left over that have to go in the second energy level. they pack in one electron at a time, one in the first s orbital, one in the first p, second p, third p. So there are 4 electrons in that outer shell that are likely to be reactive. These are called valence electrons. For nitrogen, because it's +7, we have 2 in the first energy level, and then we pack in 1 for each of the S and the P's, like I was just talking about. But then that additional 1 is going to pair in an orbit with in the first s orbit. So they would be opposite each other, but in this drawing it would be hard to write that. So a lot of times they will write them together, okay, like that. These guys are stable because they are together in an orbit. The ones that are alone are the valence electrons. All right. Now this one is oxygen. This O is actually, it's O for oxygen. The central core is this outer ring. It has +8. So 2 in the first energy level, that's the maximum. You're going to have then 6 others. You're going to pack in 1 for each of the orbitals, and then 2 for the S and the P's, the first P, and you have 2 then valence electrons. All right. So a easy way to write that is on the back of that sheet that I gave you, and that is what we call the Lewis dot formula. So take a look at that, and you can look and see, and this is showing you in the periodic table, hydrogen, helium, etc. Notice that the ones over here have all of their energy levels completely full. This makes them stable and likely to exist as a pure element in nature. These are called the noble gases.